All right, let's talk about Halley's Comet. In 2061, this rock star of the solar system is making its big comeback. And its return isn't just going to be a light show in the sky. It's a massive, once-in-a-generation chance for science. But, and this is a big but, getting up close and personal with this thing, it's one of the toughest nuts to crack in all of space exploration.
So, yeah, how do you do it? The problem is, Halley's Comet is basically driving the wrong way on the cosmic freeway, and it's doing it at an absolutely insane speed. I mean, just flying past it at high speed is one thing, but to actually pull up alongside it, match its speed, a real rendezvous, that's a completely different ballgame.
And to really get a grip on why this is so difficult, we've got to rewind the clock. Let's go back to 1986, the last time Halley swung by. We actually sent a whole fleet of spacecraft to meet it, nicknamed the Grande Armada. It was a huge deal. But here's the thing about those 1986 missions. They were basically the equivalent of trying to take a good picture of a monument while blasting past it on the highway at 100 miles an hour. You get a blurry photo, a fleeting glimpse, but that's it. For 2061, the plan is completely different. This time, we don't want to just drive by. We want to pull over, park the car, get out, and actually explore the thing for years. Yeah, that brief flyby left us with so many questions. I mean, can you believe we only saw one side of its nucleus? We have this theory that it might be two smaller comets kind of smushed together, a contact binary, a bit like that comet the Rosetta mission visited. But is it? We just don't know. And what's it like on the inside? How does it wake up and start spewing gas and dust as it gets closer to the sun? These are the big mysteries that a real rendezvous mission could finally solve. So you're probably thinking, why not just fly a spacecraft out there and, hit the brakes? Well, it's not that simple. And it all boils down to the comet's really bizarre and frankly super inconvenient orbit. See, Halley is in what scientists call a retrograde orbit. Okay, picture this. All the planets in our solar system are zipping around the sun in the same direction, counterclockwise, like cars on a giant racetrack. Halley's Comet? It decided to hop on that racetrack going the opposite way. It's flying head-on into traffic, which, from a physics standpoint, makes any potential meetup incredibly, violent. And that head-on approach creates this absolutely mind-boggling speed difference. We're talking 83.4 kilometers per second. That is the speed we would have to somehow cancel out to match its orbit. It's a colossal change in velocity, and that, right there, is the core of this whole problem. So here's the bottom line. There is no rocket on Earth, or even on the drawing board, that could possibly carry enough fuel to slam on the brakes that hard and reverse direction. It's just impossible. A direct approach is a total non-starter. So engineers had to get creative. They had to come up with a much cleverer plan. And that brings us to the plan. And honestly, it is an absolutely genius solution. It's this beautiful, elegant piece of orbital mechanics that basically uses the solar system itself as a giant tool to solve this impossible problem. Okay, so the strategy breaks down into 3 key steps. First, we launch from Earth, but, and get this, we don't head towards Halley, we actually head the other way, out towards the gas giants, Jupiter or Saturn. Step 2 is the magic trick. We use the massive gravity of one of those planets to do a slingshot maneuver. This isn't just a speed boost, it's a move that literally flips our spacecraft's direction around, putting us on the same clockwise track as the comet. And then step 3 is the long game. We fire up some super efficient electric thrusters and just cruise for years, gently, carefully, shaping our trajectory until we perfectly match Halley's orbit for a zero-speed rendezvous. Okay, but cruising around in deep space for years poses another problem: power. Solar panels like the ones the Rosetta mission famously used are fantastic when you're close to the sun. But way out by Jupiter, they're basically useless. Not to mention, they'd get sandblasted by all the dust coming off the comet. So for a mission like this, you need a different solution: a nuclear power source. We're talking about an RTG, a radioisotope generator. It uses the heat from decaying radioactive material to make electricity, which means we'd have reliable power no matter how far we are from the sun, even when we're flying right through the comet's dusty coma. All right, so we've got the grand strategy down, but the devil's always in the details. Mission planners have actually worked out a few different ways to pull this off, a few different routes, and each one has its own pros and cons. And here are the 4 main options they're looking at. You can see they're labeled J for a Jupiter flyby and S for a Saturn flyby. And the trade-offs become pretty clear when you look at it. If you use Saturn, like in the S1 path, You can get there earlier, but that means you have to launch sooner, in the early 2030s. If you use Jupiter, you buy yourself more time to get the mission ready, but you show up to the party a little bit later. So it's this really tricky balance between timing, energy, and how much science you can get done. Now this chart really highlights one of the biggest factors, launch energy. You can see that S1 path using Saturn requires way less energy to get going. And why does that matter? Well, lower energy means you can either use a smaller, cheaper rocket, or even better, you can pack more cool science instruments onto your spacecraft. It's a huge win. So when you weigh all the options, one path really stands out as the winner, the S1 trajectory. It's the most efficient, and here's the really crucial part. It gets us to the comet way back in 2056. That's a full 5 years before Halley even gets to its closest point to the sun. That means we could be there when the comet is still deep frozen and dormant, and we could watch in real time as it starts to wake up. For scientists, that is the absolute jackpot. And believe me, the scientific payoff here would be massive. But there's a catch. To pull this off, we're up against a very real and very unforgiving deadline. I mean, just think about the science we could do. We could actually watch the very first wisps of gas, like carbon monoxide, start to hiss from the surface as it warms up. We could finally create a complete, high-res 3D map of the entire nucleus. We could see cliffs crumble and dust storms swirl across its surface over months and years. We could even analyze its dust to figure out if comets like Halley might have brought water or maybe even the building blocks of life to the early Earth. It's just incredible. And to capture all this amazing stuff, the mission would carry some seriously cool new tech. For example, the proposed main camera has a field of view that's 8 times wider than the camera on the famous Rosetta mission. That is a huge leap forward, giving us a perspective we've never had before. So what does that actually mean? It means we can fit the entire comet and the space around it in a single photograph. So if the comet suddenly has an outburst and spits out a giant cloud of dust or a chunk of ice, we won't miss it. We'll see the whole event unfold and be able to trace that material right back to the exact spot on the surface it came from. That's a game changer. But, and here's the big but, look at this timeline. That perfect launch window for the S1 mission, it opens up around 2030. And the absolute drop-dead latest we can launch to catch all that early comet activity is 2040. Now that might sound like a long time away, but in the world of designing, building, testing, and launching a complex interplanetary spacecraft, trust me, that is right around the corner. And the scientists who came up with this plan don't mince words. They state it very plainly. Launching after 2040 means a severe loss of scientific knowledge. In other words, we would literally show up late and miss the most important part of the show. So the plan is on the table. The technology is within our reach. We have this incredible, once-in-a-generation chance to finally, truly understand this ancient object that has captivated humans for thousands of years. The only question left is, are we going to take it?